So this is a new day. So we're going to take a look at this. Maybe I should do this. This is the fourth lesson, right? We're going to talk about the machine learning process, because training, testing, and prediction, and artificial intelligence. So we're going to introduce something. Well, essentially, everything here is the process we want to train and use a artificial intelligence, a neural network, deep learning model. So first of all, I want to give you a look at here. First of all, I want to give you some introduction. I want to introduce machine learning, artificial intelligence, machine learning, and the deep learning. So we want to clarify the term. And then I will tell you what is the machine learning and the basic structure and the learning process of artificial neural networks. So do you guys want a 5 minutes break? Yeah, we can take a 5 minutes break. And then I'll come back and tell you about the artificial intelligence. We had a very brief introduction yesterday, but I will give you a little bit more information about the process. Since you guys, well, guess what? I assume you guys have some ideas about AI and machine learning. Since responses from most of the students seems like you need some help in understanding AI models. So I pull some materials from another course of mine. We're going to talk about it. All right. Let's have a break. We have 4 minutes left. I'll see you after a while. So let's talk about first of all, we got some terms: artificial intelligence, machine learning, deep learning. These are buzz terms, right? A lot of times people got confused with them. Definitely, yes, that's true. People got confused. So essentially what we see, artificial intelligence, machine learning, and deep learning. Artificial intelligence has the largest scope. It's a very general concept. It's essentially any program that can sense, reason, act, and adapt. That would be artificial intelligence. Initially, artificial intelligence, a big area is called expert system. Example, you want to do some health check, right? A health check. So there is some rules, and just let you say, hey, do you have a headache? You say yes. It's going to go to the next step and say, are you able to sleep, or something like that. So at the second, well, based on these rules, there is some rules, predefined the rules, and saying, hey, you're going to check this and this. Go to the lab and check a couple of things, right? And then eventually it gives a suggestion that you probably give you some health advices or do some diagnosis, whether you have some diseases or something. So that is just based on the rule. It's still artificial intelligence because it mimics human beings' intelligence, right? Well, there is another kind of, gradually when the computing technology advanced, there is another type of artificial intelligence. It's called machine learning. Well, when we say learn, that means we, based on the same program, the same procedure, but we do better and better by consuming when we learn, right, from the data. So because it's about some years ago, the data, more and more data were available. So some machine learning became pretty popular. And the same program, based on the same program, the program could work smarter and smarter because it learns. But only about 15 years ago, after if I want to say, well, the first time that modern AI caught my attention was 2013, 2014. That's about less than 15 years. So we do some deep learning. What is a deep learning? Deep learning is based on a structure called a mathematical model. That kind of, with a structure, we call it the neural networks. Neural networks essentially is a structure we saw yesterday, right? So now, that's very interesting. In professional term, artificial intelligence is a very general concept. And machine learning is the type of things that the performance can improve. The performance can improve based on consumption of data. However, many of them are still not that smart, especially you can merely collect some statistics trend, but the really smart stuff comes from the deep learning. It has been there only in about 10, 15 years. That's what I want to say. And all the actual AI we're talking about refer to this deep learning. So people talk about AI. Actually, if you ask them, 99% of the people, when they mention AI, they talk about the deep learning. So that's very funny. This is a very funny fact, right? So our focus is on the deep learning using neural networks. All right. So as we say, the artificial intelligence, it has a larger scope than machine learning. What kind of machine learning we have? There's essentially two types. Maybe some people say it's three types. I want to list the two types here. If needed, I'm going to introduce another one. Well, essentially, there is a supervised learning and unsupervised learning. Supervised learning means there is a process, there is a training process. We're going to train the data, which means, for example, we want the machine learning to classify a dog and a cat, right? So I show a picture, so the machine going to tell me this is a cat or it's a dog. Well, in order to make that happen, we need to train the mathematical model. We need to train it. What do we mean train? Train means we show the machine a picture and also we give them the answer. So we're going to show him this is a dog, this is a cat, this is a dog, this is a cat, this is a dog, this is a cat. We repeat that kind of thing with many different pictures of dogs and cats, right? And eventually, that machine gonna learn to predict it. What do you mean by predict? Predict means you don't tell the answer, you just ask, hey, is this a dog or cat? That machine gonna tell you either this is a dog or cat, right? So that's this kind of thing, we call it the supervised learning, because supervised, it's just like a teacher, right? The teacher teach you, give you the question and tell you the answer. That is supervised. If I give you the question, I don't give you the answer. That kind of training is unsupervised learning, right? Because no one supervises you. What are the unsupervised learning? Because we're human beings, right? We recognize a lot of animals in the trees based on their similarity. So we say, hey, this is what kind of a tree? This is a sheep, this is a tiger, these are tigers. Why? Because we see the similarity. Simply based on similarity. No one told us this is a tiger, right? And our scientists, human scientists, eventually they classify this. However, before we have that animal sciences, we didn't know, but we still tell them. So like horses, we want to ride on it. Cows, we want to use them to help us on agriculture activities, right? So how can we recognize them? We don't have training. We just tell the differences, the similarities based on similarities. That's unsupervised learning. A lot of times, guess what? Majority of the work is here, supervised learning. And the supervised learning, we do two things, regression and a classification. What is a regression? We did it yesterday. We want to tell what is the relation between insulin and the blood levels, right? So we plot a straight line, a linear, we assume they have a linear relations. We plot a line with the slope and intercept. So we can calculate that. So all the values are continuous. The number could be any number. There is another thing. It's called the classification. The classification means you have only a few values. They're discrete values. For example, cat or dog. Either cat or dog. There's no third way. It's not like a half dog, half cat. You can't say that, right? And for example, when you go out, do you want to bring your umbrella? Well, you can either bring it or not decision based on the weather condition, right? It's rainy or not, whether there will be heavy rain and what was the chance, whatever. You make a decision, you either bring it or not to bring it. So the machine is going to give you suggestions, bring it or not bring it, right? You can't say, hey, cut in half and bring half. So that kind of work is called what? Classification. So the regression and the classification, you have to be trained. Your mathematical model has to be trained by data. It learns from data, right? It learns from data. Why? Because we have a regression data already, but simply to say for classification, whether you want to bring umbrella, whether this is a cat or dog, you train it. You give a picture and say, this is a dog. Give another picture, second picture, you say, this is a cat. So you give them many pictures and tell them the answers. And eventually machine learns, right? And also the same thing as the whether you want to bring umbrella. If some historical data, machine going to associate the weather condition versus whether you want to bring an umbrella, right? So, and eventually it's going to give you a suggestion based on the weather condition. So that's supervised learning, and unsupervised learning is not our focus. Typically, they're relatively easy, right? It's just based on some similarity. And the similarity is some assumption. What do you mean by similar? If you talk about the 4 feet and the tail, there's so many kinds of animals out there. So you really want to, when you do this unsupervised learning, there is a lot of assumption. You can put some assumptions, right? In, I want to say, I forgot the term. Essentially, if the similarity is very high, that's going to be fall into a exact category, right? If the similarity is loosely matched, right? That means they belongs to maybe a bigger category. So the category has a structure. So as we said, deep learning is a kind of machine learning, right? So in deep learning, yes, we can perform, since deep learning is a machine learning, is a supervised learning. So we can perform regression and the classification using deep learning, right? And the deep learning is involved in what? Neural networks. So we're going to talk about artificial neural networks, convolutional neural networks, and recurrent neural networks. We're going to talk about all these in next lessons. So today we're going to focus on the first one, all right? So as I just said, initially, what is a simplest neural networks? I said yesterday, right? What is this? Y is AX plus B. What is the shape of this? Can you guys tell me? It's a curve, it's a line, linear line. Well, guess what? Did I said that yesterday? So just one neuron cell is actually doing this kind of linear regression. So that's it. So each cell does this. And also it gives a function, it's called activation function, to realize the conversion from linear to nonlinear, because the real world has a lot of, majority of the phenomena in real world, they are non-linear. So that's how we simulate the real world, right? Well, cool. That's it, right? However, let's still look at the y is equal to ax plus y, plus b, I'm sorry. So this is math. Well, the problem is we don't know what a and b is, right? Initially, you can give them a random number or zeros, whatever you want to say, right? So what is the machine learning? The job of machine learning is to learn A and B, to determine a good A and B, so that yesterday we have the slope in the diabetes, right? So that's it. That is the machine learning. The mathematical relations or models are built by human beings, scientists and engineers, especially scientists. They build those mathematical models. The data scientists, the engineers, what they work on, how to determine the A and B, because initially we don't know what is that. Gradually, this A and B gonna go to approach to a best value so that the whole machine can predict the real world better and better. That's the process of machine learning. So we need 2 steps. The first is data with answers, just like a cat. This is a dog, right? We give the picture and the answer, which is a dog or cat, and then put into a model. I want to say it's a model with, it's a mathematical model, let's say, a mathematical model. It's an algebra model, right? So after fit means training, I don't know why people use fit. The guy who wrote the program, they put a fit here because AI, there is a lot of different people, people from different subjects, different disciplines. They work in the AI area. So a lot of times their contribution, they use the term of their field to define the process. So someone say training is fitting. I don't care. But with that kind of training, essentially, if eventually you got a model with I want to say it's a boat. Let's call it a boat, right? A boat or squared or blackened, whatever you call it, a boat model. In this boat model, A and B are determined. So we can use this boat model to do prediction. The next time we say the data without answer, which means I just show the picture. I don't tell you this is a cat or dog. Using that trained model, we can do prediction. The answer should be accurate, right? Should be accurate enough, isn't it? Yep. So this is a supervised learning process. The process is we're going to do training using data to train it. What kind of data? Initially, the model is just mathematical form. All the parameters are undecided, undetermined. And the data, we have provided data with labels. We call it, sometimes we say the answers, we say it's label. We label the data. We give the answer and to the machine. And the machine should learn to adapt their parameters to an optimal value so that it does the job really good. And the next time we can utilize it. So first is training. Second is to use it or predict it. So there is some predictions. I think there is the result could be like 3 types. Number one, hot prediction and saying this is a cat or dog. And there is another chance they rank prediction, give a ranking. Most likely this is a cat. Second likely this is a dog. Or, right? Third likely something else. Well, there is another way that we use is a probability. Let's say this is a 90% of chance this is a cat and a 10% of some, it could be something else. If the chance is very high, we pick the highest chance as the result, right? As the output. You can do that. Neuron, we talked about that yesterday. There is a neuron. This neuron is essentially a linear relations. You're probably going to say, no, this is not right because you have only one x, but we have x1 and x2. If you put it in a vector in a matrix way, and it will be valid. What is this? This is a linear algebra. So I want to say even we have more than one input, it's still, we consider it's linear. Okay? And we can down degrade it into one dimension, that will be a straight line, right? If we have 2-dimensional in geometry, we can plot it like a plane, right? So the output, this is the net input. This is the sum of these 2 inputs. And the output, the response, would be a function of the net inputs that we apply a activation function that will come to the actual output or response. So very simple structure. Some examples, you want to determine this, don't worry about this. So these are some examples. The learning process, how can we determine the A and the B? Essentially, the machine learning process is, it initially will assume this is AX plus B, but we don't know A and B. By using the data sets, by using the data, we learn and eventually we determine, in this case, slope and intercept. So that's the machine learning process. And we did it last time, right? Even though we use linear regression. Again, I want to say one neuron. I'm not talking about the neural networks, just one neuron. Yes, exactly. In neural networks, each neuron is a linear regression. That does linear regression. That's true. But think about this. It's going to work with trillions of linear regression. That would be much powerful than a single linear regression, isn't it? Right. So a neural network is something like this. I don't know, like this, I want to say. If you want more readings, I put a link right over here. It's a Stanford tutorial. I'm not going to go to details, But for you guys, especially if you are very interested in this, it's a good thing to learn. But to read this, you have to understand, I think, pre-calculus and linear algebra. And it's better to have some calculus knowledge as well. So, but anyway, the structure is like this, as I just mentioned. It has input layer and output layer and some hidden layers. We don't know how many, could be any number. And in each layer, you could have different numbers of neurons. And each neuron in the front, in the previous layer, has input to current layer. They're pairized. Look at here, this pairized, right? This neuron, it receives inputs from all neurons of the previous layer. And it's going to output to all neurons of next layer. And the direction is one-dimensional. It's from left to right. There's no right to left propagation. So this is a structure. This is very famous technique. Well, what is that? Essentially, the learning process. So how does it learn? The learning process is like this. Feynman technique. You choose a concept, let's say dog and cat and dog, right? Teach it to a young person. I just tell you, this is a cat, and this is a dog, this is a cat, this is a dog. I take multiple examples. And then, right, I give you a test. You say, I give you a picture and say, hey, what is that? This is a dog or cat. I'm going to give you a test and see the difference. If you match the answer, I don't give you a point. I don't. But if you answer it incorrect, I'm going to give you a loss point. That means you lost 1 point. So every time I do this, well, so okay, so the next time we're going to come again, I'm going to ask you another question, whether this is a cat or dog. I'll give you a picture. So you answer it again. Well, guess what? In here, I'm going to compare the answer versus the correct answer versus your answer, your response. So each time you learn between this from the difference, whenever you're wrong, you're going to learn, right? If you're right, you're good to go. Don't change anything. So your knowledge is good. But when you are wrong, I'm going to give you 1 point and say, hey, you lost 1 point. That's a loss point. We call it the loss function. So that's how you learn, because we only want to learn when the machine did it wrong, isn't it? Right? So that's why I don't give you, this is different from human being. The human being is, if your answer is right, I give you a credit. If you don't answer it, I don't give you any credit. No, that's not right. For machine, I have to tell you, you need to change since you're wrong. Or otherwise, you don't need to change. You did it right. We don't have to, because machine is not emotional. How can I say that? We don't need to encourage it. We just tell him, frankly, saying, you're right or you're wrong. If you're wrong, change it. You actually can do that with Google Teachable Machine. I don't know, maybe, let me think about it, what I'm going to provide you with some learning process. Maybe we can do the data analysis the next time. But the Google Teachable Machine is a really good one. Probably we can do a lab like this. It's a great tool to learn machine learning and artificial intelligence. So maybe we can do that. There are some cool models that you can do. There is 2 very famous models that we can do. One is the face mesh. Essentially, it's AI going to track the key points, 184 key points on your face. And let's say you're driving, you're driving and talking with others, or you feel like a sleepy. So based on your mouth, right, and also your eye, how can I say that? Right, eye top, eye button. If you're blinking or you close it, or the width is very small, smaller than usual, I'm going to assume that AI can assume you're sleepy. It's going to give you a warning while you're driving, right? And also, there is another one. There is a lot of applications that you can make in the face mesh. There is another one. It's called the PostNet. Essentially, it's going to give you the key points of your skeleton. So the AI going to do this. One of my students won the best of category, the first grand prize at ISEF last year. he did the Parkinson's diseases, because the Parkinson's diseases is a diseases of senior people. So there is a lot of symptoms, like their walking is unbalanced, and their back is, I want to say, hatched, bended, and their hands are tremor, shaking very often. So all these can be measured by AI. And that was a really good ISAF project, a research project. Obviously, he did a lot of extra credit research, but the basic idea, they use this techniques post-net, right? I think this is what we mentioned before. One thing is, I just want to give you a flow of how the machine learning happened. So this is the one. Well, this is an analogy, right? Because this is a biological neuron. But in our case, we just say, hey, there is a neuron. We just assume this is a neuron. Actually, it's a math. It's mathematics, right? Again, even though this is mathematics, but for neural networks, mathematician does not solve a lot of problems. They can't derive it. It's really hard to calculate it. Just we have to do training. That's why. So this is a neuron. We got some inputs, whatever the inputs, we got some weights. This is called the weights, right? Yeah. So this is the actual calculations. You can do this, you add them together, that would be 9.74. That would be the net input. Yeah, net input. The only way is we use this kind of formula, right? AX plus B, or whatever. If you want to say it in the algebra way, you can say A1, X1, A2, X2, and the plus B, because B is always a constant. Even B1 plus B2, that would be a constant. We just use 1B. So this is the one. And then we go to here. So we add them together. That's right. Oh, this is the bias. We add bias, and eventually we got the value of 3.74. So this is the calculation. If you want to do that, this is pretty simple stuff, right? So the net input would be 3.70. So the next time we're going to apply activation function. By apply that nonlinear activation function, the result would be, I feel like I still need a couple of things. By apply this activation function, that should have a value. So the output value should have a number. Number 5. Look at here. This is number 5, right? Number 5. What it says, yeah, we apply activation function to capture the linear or nonlinear relations. Oh, more about it can be found in the next one. So we do this kind of thing. So, well, so I think this is a process just for one neuron. So we apply the whole process, this whole process for all these, and only one. It can have multiple hidden layers. So we're going to apply all these. And eventually we got something. We got the output. Well, the thing is, initially the output doesn't make sense because the model, right, does not learn. All the parameters are random set, or maybe zero set or random set. So the problem is it doesn't work. So we have our error, our loss function going to be value from our loss function. The loss would be very high. So that is where we're going to force the very last layer to learn. I mean, maybe I have a better one. Just 1 second. No, I think, right, this is just for one cell. What it says is we can apply this process for all of them, for all neurons. Let me see. I think I have another one, an even better one. The next slide is to describe the whole thing. So if you do that process, that means you have an output. But your output could be right or could be wrong. So we're going to use if you look at here, this is now, our view would be here. Instead of looking just one of the neurons, we look at the whole thing. We have input. These are the neural networks. And then we have the output layer. So we have a predicted. So this is what the neural networks think, the answer. And we're going to compare with the true answer, right? No, hold on. Predicted output, the true answer. the correct answer. We compare them and we only count the errors. So we got the loss, isn't it? We calculate the loss. So this is the way we want to do. For example, you predicted the actual is yes, and you predicted yes, that's good. And the actual is yes, you predict the machine predicted a no, right? Or otherwise, so that means these are correct. This is correct, but we lost 2 times, right? These are the loss. Based on the loss, we can change something. Look at here. If we know what we were not correct, that is the time we're going to adjust the parameters. That means the parameters were not good, right? Not good enough, at least. So what we do is, okay, so what we do is the next time it's going to come to the place that how it learns, how the neuron adjusts their weights. Let me see whether this is a...
Here, we tackle backpropagation, the core algorithm behind how neural networks learn. After a quick recap for where we are, the first thing I'll do is an intuitive walkthrough for what the algorithm is actually doing, without any reference to the formulas. Then, for those of you who do want to dive into the math, the next video goes into the calculus underlying all this. If you watched the last 2 videos, or if you're just jumping in with the appropriate background, you know what a neural network is, and how it feeds forward information. Here we're doing the classic example of recognizing handwritten digits, whose pixel values get fed into the first layer of the network with 784 neurons, and I've been showing a network with 2 hidden layers having just 16 neurons each, and an output layer of 10 neurons, indicating which digit the network is choosing as its answer. I'm also expecting you to understand gradient descent, as described in the last video, and how what we mean by learning is that we want to find which weights and biases minimize a certain cost function. As a quick reminder, for the cost of a single training example, what you do is take the output that the network gives, along with the output that you wanted it to give, and you just add up the squares of the differences between each component. Doing this for all of your tens of thousands of training examples and averaging the results, this gives you the total cost of the network. And as if that's not enough to think about, as described in the last video, the thing that we're looking for is the negative gradient of this cost function, which tells you how you need to change all of the weights and biases, all of these connections, so as to most efficiently decrease the cost. Backpropagation, the topic of this video, is an algorithm for computing that crazy complicated gradient. And the one idea from the last video that I really want you to hold firmly in your mind right now is that because thinking of the gradient vector as a direction in 13,000 dimensions is, to put it lightly, beyond the scope of our imaginations, there's another way you can think about it. The magnitude of each component here is telling you how sensitive the cost function is to each weight and bias. For example, let's say you go through the process I'm about to describe and you compute the negative gradient, and the component associated with the weight on this edge here comes out to be 3.2, while the component associated with this edge here comes out as 0.1. The way you would interpret that is that the cost of the function is 32 times more sensitive to changes in that first weight. So if you were to wiggle that value just a little bit, it's going to cause some change to the cost, and that change is 32 times greater than what the same wiggle to that second weight would give. Personally, when I was first learning about backpropagation, I think the most confusing aspect was just the notation and the index chasing of it all. But once you unwrap what each part of this algorithm is really doing, each individual effect that it's having is actually pretty intuitive. It's just that there's a lot of little adjustments getting layered on top of each other. So I'm going to start things off here with a complete disregard for the notation, and just step through those effects that each training example is having on the weights and biases. Because the cost function involves averaging a certain cost per example over all the tens of thousands of training examples, the way that we adjust the weights and biases for a single gradient descent step also depends on every single example. Or rather, in principle it should, but for computational efficiency, we're going to do a little trick later to keep you from needing to hit every single example for every single step. In either case, right now, all we're going to do is focus our attention on one single example, this image of a 2. What effect should this one training example have on how the weights and biases get adjusted? Let's say we're at a point where the network is not well trained yet, so the activations in the output are going to look pretty random, maybe something like 0.5, 0.8, 0.2, on and on. Now we can't directly change those activations, we only have influence on the weights and biases, but it is helpful to keep track of which adjustments we wish should take place to that output layer. And since we want it to classify the image as a 2, we want that third value to get nudged up, while all of the others get nudged down. Moreover, the sizes of these nudges should be proportional to how far away each current value is from its target value. For example, the increase to that number 2 neuron's activation is in a sense more important than the decrease to the number 8 neuron, which is already pretty close to where it should be. So zooming in further, let's focus just on this one neuron, the one whose activation we wish to increase. Remember, that activation is defined as a certain weighted sum of all of the activations in the previous layer, plus a bias, which is all then plugged into something like the sigmoid squishification function, or a ReLU. So there are 3 different avenues that can team up together to help increase that activation. You can increase the bias, you can increase the weights, and you can change the activations from the previous layer. Focusing just on how the weights should be adjusted, notice how the weights actually have differing levels of influence. The connections with the brightest neurons from the preceding layer have the biggest effect, since those weights are multiplied by larger activation values. So if you were to increase one of those weights, it actually has a stronger influence on the ultimate cost function than increasing the weights of connections with dimmer neurons, at least as far as this one training example is concerned. Remember, when we talk about gradient descent, we don't just care about whether each component should get nudged up or down, we care about which ones give you the most bang for your buck. This, by the way, is at least somewhat reminiscent of a theory in neuroscience for how biological networks of neurons learn, Hebbian theory, often summed up in the phrase, neurons that fire together wire together. Here, the biggest increases to weights, the biggest strengthening of connections, happens between neurons which are the most active and the ones which we wish to become more active. In a sense, the neurons that are firing while seeing a 2 get more strongly linked to those firing when thinking about a 2. To be clear, I really am not in a position to make statements one way or another about whether artificial networks of neurons behave anything like biological brains, and this fires together, wire together idea comes with a couple meaningful asterisks. But, taken as a very loose analogy, I do find it interesting to note. Anyway, the third way that we can help increase this neuron's activation is by changing all the activations in the previous layer. Namely, if everything connected to that digit 2 neuron with a positive weight got brighter, and if everything connected with a negative weight got dimmer, then that digit 2 neuron would become more active. And similar to the weight changes, you're going to get the most bang for your buck by seeking changes that are proportional to the size of the corresponding weights. Now, of course, we cannot directly influence those activations. We only have control over the weights and biases. But just as with the last layer, it's helpful to just keep a note of what those desired changes are. But keep in mind, zooming out one step here, this is only what that digit 2 output neuron wants. Remember, we also want all of the other neurons in the last layer to become less active. And each of those other output neurons has its own thoughts about what should happen to that second to last layer. So, the desire of this digit 2 neuron is added together with the desires of all the other output neurons for what should happen to this second to last layer. Again, in proportion to the corresponding weights, and in proportion to how much each of those neurons needs to change. This right here is where the idea of propagating backwards comes in. By adding together all these desired effects, you basically get a list of nudges that you want to happen to the second to last layer. And once you have those, you can recursively apply the same process to the relevant weights and biases that determine those values, repeating the same process I just walked through and moving backwards through the network. And zooming out a bit further, remember that this is all just how a single training example wishes to nudge each one of those weights and biases. If we only listened to what that 2 wanted, the network would ultimately be incentivized just to classify all images as a 2. So what you do is you go through this same backprop routine for every other training example, recording how each of them would like to change the weights and the biases, and you average together those desired changes. This collection here of the averaged nudges to each weight and bias is, loosely speaking, the negative gradient of the cost function referenced in the last video, or at least something proportional to it. I say loosely speaking only because I have yet to get quantitatively precise about those nudges. But if you understood every change that I just referenced, why some are proportionally bigger than others, and how they all need to be added together, you understand the mechanics for what backpropagation is actually doing. By the way, in practice, it takes computers an extremely long time to add up the influence of every single training example, every single gradient descent step. So here's what's commonly done instead. You randomly shuffle your training data and then divide it into a whole bunch of mini batches, let's say each one having 100 training examples. Then you compute a step according to the mini batch. It's not going to be the actual gradient of the cost function, which depends on all of the training data, not this tiny subset. So it's not the most efficient step downhill, but each mini batch does give you a pretty good approximation, and more importantly, it gives you a significant computational speedup. If you were to plot the trajectory of your network under the relevant cost surface, it would be a little more like a drunk man stumbling aimlessly down a hill, but taking quick steps, rather than a carefully calculating man determining the exact downhill direction of each step before taking a very slow and careful step in that direction. This technique is referred to as stochastic gradient descent. There's kind of a lot going on here, so let's just sum it up for ourselves, shall we? Backpropagation is the algorithm for determining how a single training example would like to nudge the weights and biases, not just in terms of whether they should go up or down, but in terms of what relative proportions to those changes cause the most rapid decrease to the cost. A true gradient descent step would involve doing this for all your tens and thousands of training examples and averaging the desired changes that you get. But that's computationally slow. So instead, you randomly subdivide the data into these mini batches and compute each step with respect to a mini batch. Repeatedly going through all of the mini batches and making these adjustments, you will converge towards a local minimum of the cost function, which is to say your network is going to end up doing a really good job on the training examples. So with all of that said, every line of code that would go into implementing backprop actually corresponds with something that you have now seen, at least in informal terms. But sometimes knowing what the math does is only half the battle, and just representing the damn thing is where it gets all muddled and confusing. So, for those of you who do want to go deeper, the next video goes through the same ideas that were just presented here, but in terms of the underlying calculus, which should hopefully make it a little more familiar as you see the topic in other resources. Before that, one thing worth emphasizing is that for this algorithm to work, and this goes for all sorts of machine learning beyond just neural networks, you need a lot of training data. In our case, one thing that makes handwritten digits such a nice example is that there exists the MNIST database with topic and other resources.
Okay, so this is what I want to say. To summarize this process, the learning process, okay, so in order to train the model, right, there is two kind of like a path. The first path is we put some inputs. For example, this is an image of numbers, right? We're gonna do this. We're gonna do this. This is our homework. This will be our homework. Not our homework. Yeah, will be our homework. That's right. So we put the image, input the image. We let it train. Initially, all the weights and values, they're random. Okay, they're random set. So the answers would be random, right? Won't be correct. It's just like a random guess. Okay, so we compare the output, the prediction versus the actual answer. Because we know the answer, this is like a 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Those digits. So we compare with the answers, we got the loss. Based on the loss, we're gonna enforce what? The change of the weight and bias of the previous layer. Okay, so initially the very last layer in the hidden layer, right? The very last layer of neurons. in the hidden layer, in the hidden layers, right? Okay, in order to achieve that, we need to update the weight and bias of the previous layer, which means the second last layer in the hidden layer. And this process continue that we're gonna update the third last layer, the weights and bias of the third last layer, all the way back to the first layer, first hidden layer. All right. So what does this mean? This means back propagation. So the learning process happens in the what? In the back propagation. So how can we do that? It's actually not a process. It is a process, but it's based on some mathematics, deep mathematics. You need a lot of you need to understand, deeply understand, calculus in order to perform that. So, all right. So to train the model, there is 3 steps. Number 1, what? Give a test, which means I just give you an input data, like an image, cat or dog, right? Or digit, 0 to 9, some digit. Okay, let it go. Okay, I get the response from the machine, and that's the first step. That it is called a forward. It's called a feed-forward propagation. That means from left to right. Okay, the signal from left to right. All right, the second step is to calculate the loss. What is the loss, right? The loss, when you have a loss, I'm going to give you some give you a notes. Okay, if your answer is correct, there's no praise, no credit, right? So that's the way we train the machine. Okay, so that's the second step. The third step is assume I want to correct the answer. Okay, what I should do with the latest layer. I mean, the last layer. I mean, the previous layer. Okay, in order to update the last previous layer, what I have to do for the second to last layer, all the way to the first layer. So that's the process. Okay, so this is a learning, right? When we say learning, that means you're going to do it better. Okay, the back propagation is actually adjust the weights and bias in order to achieve a better performance for the AI model, right? So that's the if you understand this process, we can do some machine learning training. Yeah, let's do that. Okay, so this is a really good video. If you guys have time, yeah, I would encourage you to watch it for a couple of times, because one time probably not enough to understand this. And amazing. I mean, this video is amazing. It's really, really good. Very concise, very eye-catching. So I love to watch it. And actually, I watch it a lot of times. It's not very long. It's about like 10-15 minutes each. So yeah, just do it. Okay, now I want you to do an experiment with me. It's going to be very fast. Go just type Google Teachable Machine. So very likely you're going to see the Google Teachable Machine in the first item of your search. I think there is a good question. And how do you know what to change and how much to change? That is about the math. That's about the send you this link. That will be based on, if you watch this again, it's going to talk about the math in the next chapter of this. I'm not showing a lot of mathematics over here. Just want to tell you the process. Why? Because as a high school student, I do not really require you to understand the math. If you know this kind of process, that will be sufficient for us to do programming next time. This is our homework. We're going to do it. I will give you detailed information next time. And we're going to give you an example you can follow. All right, can you guys open this Go Teachable machine? I send you a link. I want you to confirm if you open the Teachable machine, just type a TM. That means Teachable machine. I want to make sure you are on this page. DJ, all right, it's fine. What about the others? I don't see all of you guys. Are you all still there? So you know, to here, there is a lot of information. You guys gonna read it because we have like less than 10 minutes, right? I'll go get started. Just click here. And you do post project. See here, post estimation. See here, right? Audio, I can do audio stuff, but let's do the first one, image project. There's a standard image model or something. Just click standard. Don't use this embedded image. The embedded image, you can use it for the future. When we build a microprocessor, we can download the model to the microprocessor. But now we're using PC or regular computer. So we use standard image processor. Oh, look at here. So there is a webcam. I have a webcam. I want to open it. If you see it, I'm here. I'm here. In order to show my different looking, I just put the cap, right? In order to show different things. I have two things. I have a cap. I have sunglasses. Look at here. I'm going to wear them different. I mean, as different groups. It's like two different persons or whatever. Or a person with different makeup. Oh, let's do this. Now, do this. Can you how to record? If you look at here, these are the pictures. I'm here, but not exactly the same, right? I try to shift my hand, that kind of thing. I have taken 40 images already. This is a class 1. I want to say cat. That's cat, right? These are me with caps. If you want to do something else, definitely you can do that. You can put like two kinds of fruit, and you can do the same thing. I just want to give you a quick view. Oh, there is a class 2. You can name it. No, hold on a second. I have sunglasses. So now I'm wearing sunglasses. Let's make a different looking. So if you look at here, I got like 55 images. That's my I wear my sunglasses, right? So I want to say this is a sunglasses, whatever, sunglasses, right? So what I do is look at here. What is the label? Can you guys tell me what is the label? What is the data? What is data? Data is the images, right? It's the pictures, these images, right? These images. How many images do I have? I have 40 and 55, isn't it? What is the label? Answer. Answer is the group name, right? Cap or sunglasses. I give this name. Now I do training. Look at here. I do train the model. It says preparing training data. It takes a while. Looks like it's training epochs like to 50, right? What does that mean? That means these data are being used for 50 times. Why? This is just like a human beings, right? If we read something, a lot of things we're going to read twice, maybe the third time and 3 times, isn't it? Computer is not really enough thought. It's going to train for 50 times in order to grasp the idea, the feature, the characteristics of the data. Anyway, let's do this. Look at here. Epochs means number of times we're going to use the data. If you mouse over, it's going to explain. Mouse over the question mark, it's going to tell you what is the epochs means, concepts. The batch file, that's essentially how many pictures you input at a time. Remember, in the video, they input 1 picture at a time. You actually can input many, like 16 pictures at a time for training. That's okay. And the learning rate, actually, we don't want the learning rate to be very large. Every time we just do a little bit towards the right direction. If you don't want to do like a big step every time, we don't want to do that. Maybe initially we want a big step, and eventually we want smaller steps in order to fine tuning, right? So there is some other strategies. For now, our learning rate is fixed. This is a simple machine, not that complex. Smarter machine may have like variable learning rate. If you want to hit the under hood, more stuff right over here, just doing that. We learn here what is the accuracy, what is a confusing matrix. It's the curve, the learning curve. Seems like this is like 2-3 times the performance has already been pretty good because my background and my post is very similar. If I do like very wide, I have like different background, different posts. It's gonna take more time to train. So, but anyway, there is something you can look at it, and if you click this question stuff, question mark, mouse over, it's gonna explain what is the confusing matrix and accuracy. Right? If you wanna click here, it's gonna pop up for more information. Seems like it captured like testing. It tested the 15 cases, 6 were capped, and 6 when I actually wear the cap, predicted all correct. This is the same when I wear sunglasses. Seems like the prediction is pretty accurate here. Sometimes you wear a cap, the machine tells you you wear sunglasses. That means it's right. Initially, it's pretty random, but it's a good training. The performance would be pretty good. So I think this is what I want to say about. I'm gonna close this thing. All right. So see here, if I wear the cap, it's gonna be cap. If I don't, instead of I put my sunglasses, it's gonna say sunglasses. Right? So that is the model. It's actually prediction. It's gonna give us a real-time prediction, right? You can export your model. You can export your model, right? So how to export your model? I might want you to do a thing. TensorFlow, let's do this. Using this, TensorFlow.js, this is JavaScript. There is a upload model right over here. Click here. So it's going to take a while. It say uploading. Now it says it's already done. There is a link right over here. You can copy. Look at here. Copy this link. This link means the trained model is uploaded on the website, on their Google Teachable Machine website. And I can share this screen with everybody. Let me type it for you. If you should be able to see my screen, to see this URL, you can open it. This will work for you as well. If you use a cap, use the sunglasses, it's going to tell you. Or otherwise, you can train a apple and orange, right? That model can send this link to everyone that people can use. You have already made a machine learning model. So that's number one. This is number one. Remember, this is your lab. Your homework, click on here. Click on the TensorFlow. This TensorFlow is Python. Look at here. You can either use Keras or OpenCV. Maybe you should open OpenCV. Paste this to your Colab and make a machine learning model of yours. You know what I'm saying? This is your lab and your homework. The lab you just repeat. It's pretty straightforward. You do whatever I did, right? And you use this. Load a JavaScript, load the front-end script onto the Google Teachable Machine website. You get a shareable link so that you just submit your lab on this. Just submit your URL. I just open it. If I'm able to open it and do something, tell me what you want to do. You can classify anything you want, right? That would be your homework. Now, your homework assignment, that's your lab. Your homework assignment, click on the TensorFlow. You download your model. You can either use whatever, you can download it. You can select things. My suggestion is you can use this, right? The save model. Do you want a save model? By the way, you can use save model and select the OpenCV Keras or download it. Make it work in your Colab. In your Google Colab. That's your homework. All right. That's all I need to do. That's all for today. And any questions? Yesterday's class, the recording is there already. I see Han. You're looking for today's video was available yesterday. And today I'm going to make it as soon as I can. maybe it takes a couple of hours because the Zoom gonna process the data for pretty much like an hour or maybe more than an hour. And then I need to manually load to the YouTube and I need to edit it. I'm gonna cut some like white space, right? It's already there for lesson 3. So can I put the stuff in the Discord? What kind of stuff you want me to put in Discord? Everything in the master document. So you're gonna specify what you need. I can copy that for you. I think Yuan Zhi, the sense of your homework assignment. It's not that, it's pretty straightforward. You just make that code work. It should work, but maybe some like you're gonna adjust some parameters like path, dictionary or something like that. Just try it. Just try it. You should develop your ability for programming. So programming is still a skill. You need to understand it in order to be a good programmer of next generation. Probably, I don't think the developer gonna actually type the code, but you should be able to guide the AI to develop the code. All right. So okay. Well, just one second.